The de Havilland Dash-8 is a commercial transport airplane designed to accommodate between 36 and 50 passengers in wide-bodied comfort. The Ground Test Department is pleased to show you their contribution to the success of the program, and we also wish you to share some of our fun. About 3 years before the aircraft's maiden flight, work started on a test plan and initial test designs in the ground test engineering offices. Full-scale mock-ups and preliminary test specimens were built in the development shop. We have a saying, in here we make them, next door we break them. This is a structural test area where many of the tests were conducted. Early in the test program, before the aircraft design details were established, small elements of the aircraft structure are tested. Here, test specimens are being prepared for crippling allowable or crushing tests on an element of wing structure. After determining the crippling allowable load on test, the results are corrected using a computer program to correct for dimensional and material variations. These loads are fundamental to the stress groups analysis. 187 test specimens, similar to the one shown, were tested for the Dash-8 program. About 400 detailed static tests of various types were conducted before March 86 as part of the Dash-8 structural test program. Starting early in the DHC-8 program, the complete hydraulic system was thoroughly tested through a phase of development, followed by a flight-by-flight endurance test of the final system configuration. The work was accomplished on a ground test facility colloquially named the Iron Bird. Commercial hydraulic pumps supply power to the test rig. In the absence of engines, the aircraft main hydraulic pumps are being accelerated by simulated power levers which control pump speed through electro-hydraulic servo loops. The flight-by-flight endurance test is controlled by a computer and is monitored by engineers at the control station. Periodic checks of the specimen are made during cycling. The simulated landing gear represents aircraft assemblies with respect to true geometry, mass, and moment of inertia. Actual aircraft parts are used for the uplocks, downlocks, door mechanisms, and all hydraulic components. Typical of the rig build concept is the nose gear assembly, mounted at its true aircraft position on a rigid steel support frame. As with the main landing gear, a loading jack is attached to the leg. Pressure is adjusted to provide the required simulated aerodynamic load. Appropriate loads are also applied to the door linkages. This procedure shows emergency use of the hand pump, which extends the main gear to the downlock position, overcoming air drag adverse aerodynamic forces. By contrast, free fall of the nose gear is assisted by the drag force. By means of air loading jacks attached to the flap surfaces by chains, representative aerodynamic loads are applied to the flap system mechanism. By using two chains at each flap attachment position, the correct load vector is applied. The mechanism also allows for changes in the center of pressure during the traverse. Jack loads are varied by means of air pressure regulating valves controlled by linear cams. A test quadrant allows the rudder position to be observed from the flight deck. The rudder, hydraulic servo actuator, and input mechanism operate a dummy rudder of correct moment of inertia. A hydraulic loading jack provides simulated aerodynamic load. Loading for the flight spoilers is provided by torsion bars connected to the spoiler input linkages by means of chains and sprockets. The two aircraft servo actuators in each wing are operated by rods connected to a common quadrant. The cable system from the pilot's handwheel is included as part of the test specimen. Ground spoiler loads are also provided by torsion bars. During the endurance test, flight controls are operated by commercial hydraulic jacks attached to the control cables. Other components, such as brake control valves, are operated pneumatically. Mechanically operated components, such as the elevator disconnect, are also tested on the Iron Bird. As the pumps shut down, we end our visit to the Iron Bird. The fuel system is an example of many other systems included in the ground test program. This test rig incorporates a closely simulated wing integral fuel tank, complete with pumps, valves, piping, and electrics. Gantries and winches enabled assessment at various pitch and roll combinations. System performance was thoroughly checked out, including engine feed, fuel transfer, gauging, and refueling. A wing fuel tank proof pressure test was conducted on the static test specimen prior to assembly to the fuse. The wing was filled with fuel and pressurized to 4 psi using the manometer tower shown to the left of your screen. Other system tests require access to a production aircraft. Here, the elevator control is operated under load over full travel. Similar tests to those on the elevator were conducted on the aileron, flight spoilers, and rudder control circuits. 1.5 airframes from the first batch of aircraft were built for the static test program. Loading lugs were built in during construction. The airframes were assembled into 3 test specimens to allow testing to proceed on 3 fronts simultaneously. The airframes were completed inside the steel test frames, and the specimens were delivered incomplete to enable us to get an early start in assembling the test. Fixtures such as dummy fuse extensions and steel bulkheads were attached to the specimens while airframe details were being finalized. To enable cabin pressurization to 12 psi to be conducted safely at a remote site on the airfield, the front fuse was tested in a mobile test rig. Back in the test building, the wing fuselage and the rear fuselage airframes are being prepared for the first of 28 major static cases to be conducted. And time passes quickly as aircraft number 1 is being prepared for its first flight. We take a brief pause from the ground test program as most of the de Havilland employees watch anxiously as Bob Fowler and crew take the Dash 8 out for its first flight. This sketch shows the loading arrangement used for the critical wing bending case that follows. We pull up on the wings and down on the fuse, simulating a loading condition 1.5 times more severe than the worst turbulence an aircraft is ever likely to encounter. This wing bending case to 112% was similar to a wing bending case to 100% conducted just after first flight. 29 similar major static tests were conducted before a type approval certificate allowing passengers to be carried was granted by Transport Canada. Loads were applied to the aircraft using hydraulic cylinders controlled from the load maintainers seen here. Watch closely as the wing deflection is captured by time-lapse photography at the lower levels. As load is applied, deflections and strains are monitored very carefully in case there are indications of impending failure. Members of the design and stress group work along with us, monitoring the results from the 700 strain gauges as the test progresses. During the static test program, 1,500 strain gauges were installed on the 3 specimens. At the higher loads, ultimate strength is eroded away with time. We have now gone beyond the point of no return, and loading must continue in a steady, controlled manner. Listen carefully now, as the cracks and bangs indicate the high strains locked in the structure and the odd rivet popping. Tension increases. Will the wing break?
110.
It's already buckled. You see that?
111.
Good.
111. It didn't break.
Congratulations, Michael. You built a good flare plane.
Maybe.
We're coming down from 111% back down to 0.
The team breathes a sigh of relief. For the stressmen and designers, the wing did not break. And for the test crew, the test has been completed as planned. The wing has returned to its original position after being deflected over 62 inches. After jubilation, it's back to work again testing structures with simulated fatigue cracks, otherwise known as fail-safe tests. Aircraft share the skies with birds of the feathered variety, and as you are probably aware, they do not always get along together. To look after man's interest, we shoot 4 or 8 pound chickens at sections of aircraft. The easier way is to fire freshly thawed chickens from a large air gun at the National Research Council Bird Impact Facility in Ottawa. This sketch indicates the sequence and points of impact for the series of bird impact shots we're about to show you. Film from 2 cameras are used for each shot. The impacts were filmed at 6,000 frames per second and projected at 24 frames per second for the slow motion effect. The chicken is wrapped in linen to ensure that the bird flies straight at the target cross. Observe the window frame breaking, allowing the debris to enter the flight compartment. The specimen failed the test. In this shot, the window shattered. Severe spalling from the inner pane would probably have ended up in the pilot's face, and this specimen failed the test. This specimen passed. One of the 2 structural plies of glass failed, but the pressure tests show that 1 ply will contain the internal cabin pressure. The glass did not spall. Though the chicken liquefied and would have extruded over the pilot's head, it was not considered hazardous. To ensure that the impact would not leave the elevator in a hazardous condition, an 8-pound bird is fired. The tip of the tailplane was deflected back about 8 inches. Observe how the leading edge is gathered in, and although damage was severe, it was such that a critical flutter condition would not occur in flight. The bird passes through the front spar into the horizontal stabilizer. Following impact, flying loads were applied to the damaged horizontal stabilizer without failure. Thus, the specimen passed the test. The impact flattens the leading edge against the spar, and watch carefully as the impact deforms the structure, but the bird does not penetrate the fuel tank. During the program, about 75 bird impact tests were conducted. You are probably familiar with cards similar to this. To ensure that there are no unpleasant surprises in an emergency, we conducted unofficial evacuation tests on the 5th aircraft.
Well, welcome aboard, everybody. We ask you to become familiar with the location and operation of the emergency exits by reading the cards provided in the seat pockets in front of you. When the captain asks you to leave the aircraft, we want everyone to get out of the aircraft with a realistic sense of urgency through any door on the right-hand side.
Emergency, emergency, everybody leave.
Official evacuation tests are conducted in the dark of night under closely controlled conditions. The evacuation tests shown were not certification tests, which allowed us to take advantage of daylight to record what you can now see.
This way, Glenn. This way. What that way? Yeah.
You go out there. You go out there. You go out there.
This way.
You go out there. You go out the front, please.
This way. Keep moving. Keep moving.
The test was a success in that all the passengers got out well within the desired time and broadened our understanding of the problems associated with evacuation. On September the 28th, 1984, just ahead of schedule, a type approval certificate was granted to de Havilland for the DHC-8, clearing the airplane to enter commercial airline service. On October the 16th, 1984, fatigue testing began on airframe number 4. Apart from stops for inspections and repairs, the specimen is loaded continuously 24 hours a day, 7 days a week. The aircraft flies through 6 different flight types, in which all loading conditions affecting the wing and fuselage are simulated. Other aircraft components, such as nacelle, flaps, tailplane, and cabin pressure cycle items, such as bulkheads and a canopy, are tested separately. Loads are applied by means of 28 hydraulic jacks attached to parts of the fuselage, wings, nacelles, and tail. Here, a test engineer checks the hydraulic pumps and ensures that the fluid is at normal operating pressure. Loads are controlled by a computer, which at the same time will shut down the test if a significant failure has occurred in the aircraft or in the system itself. Let's try to follow the aircraft through a flight. As we join the aircraft, it has just taken off and the wings are being deflected by vertical gusts. The aircraft is inspected externally every 2,000 flights and internally every 10,000 flights. It has been found damage is more easily detected when the aircraft is being loaded, and hence we see a test engineer looking for cracks during an external inspection. As the flight progresses, lateral gusts cause the tail to be deflected to either side. Here we see a close-up of the dummy tailplane arrangement used to load the aircraft's fin. Fuselage loads react to loads applied to the flying surfaces as the flight continues. Here, a jack is applying load to the fuselage. The computer commands a servo valve to allow an amount of pressure corresponding to the required load into the jack. A load cell measures the load and sends feedback to the computer so it can adjust the jack to reduce the loading errors. An air valve adds air to maintain cabin pressure during the airborne phase of the flight. The aircraft lands and the nacelle noses down as the pilot applies the brakes, bringing us to the end of the flight and to the taxiing moves. Testing continues, and after 18 months, over 70,000 flights have been simulated on the major fatigue test. During the flap fatigue tests, 264,000 flights were simulated on the outboard flap and 384,000 flights on the inboard flap. The tailplane and the top of the fin are being tested here. A total of 66,000 flights had been simulated by March 1986. Loads are applied using a mechanically programmed hydraulic load maintainer. This must be one of our tiniest specimens.